Welcome back to this NPTEL online certification course in molecular rearrangement and reactive intermediates. In the last couple of classes, I talk about the organolithium, organomagnesium, and in the last class, I talk about organocopper. And in the today's class, I am going to talk about organozinc. So organozinc is also very important, and you will find a lot of the name reaction from there. So I want to start with the introduction and some of the structures and some of the different type of organozinc compounds, their preparation, what are the different methods to prepare them. Then I am going to talk about the reaction of organozinc compounds, okay. That is the important thing. So first thing is this, the discovery. Again, I think before I talk about any of the organometallic reagent, I start with what is the first compound isolated, or what is the, and when, what is the timeline. So again, you are seeing that all these organometallic compound, I talk about organocopper, and you have seen before on the organolithiums and everything, it was done in the 18th century, correct. So you have to understand that these type of organometallic compounds are present. So we found out in a long back, and there are a rich history for these organometallic compounds. So Edward Frankland actually prepared the first organozinc compound called diethyl zinc. Okay, if you have not used this in the laboratory, this is a very volatile and a pyrophoric colorless compound. So once you take this diethyl zinc outside the air, it will start catching fire. Again, you can see here we are talking about a organozinc. Again, from the definition of organozinc, there will be a zinc with the organic part, correct. So this is a diethyl zinc. Okay, it was synthesized from two equivalent of ethyl iodide and zinc. So it's from a zinc metal. Again, we are going to understand about this part a little bit, that what type of zinc we are talking about, and what are the different variation. Again, organozinc cases, we are saying that zinc 2 here mostly, and then it can adopt a different type of octahedral, tetrahedral and pentacoordinated geometries are well known. Okay, so these are the different type of coordination geometry well known with organozinc. And you can see the coordination geometry are guided by the electrostatic and steric interaction. So these are the two important factors which guide it. It will be octahedral, tetrahedral or the pentacoordinate. And again, as the 3D orbital of zinc is filled, so the ligand field does not exist. I think if you know about the ligand field theory, I think you can clearly understand that. The dialkyl zinc is monomeric with a linear coordination. Okay, at the zinc atom possesses zero dipole moment. You can see there is dialkyl zinc, so it possesses zero dipole moment. Okay, so now we are going to talk about the different things. So here it is mentioned, it is soluble in non-polar hexane solvent, and it has a low affinity towards the ethereal solvent. Okay. So now we are going to learn about the preparation, and you are going to see majorly the tetrahydrofuran. You see that we used the tetrahydrofuran in the lab for the synthesis of organozinc, also diethyl ether. Okay, sometime you will see some sort of non-polar solvent, but majorly you will see the this type of ethereal solvent. Again, the bond between the carbon zinc. So again, I think every time when I talk about this type of organometallic reagent, I talk about these important things, the difference in electronegativity. Because once you go from organolithium, from Gignard to copper to zinc, in this direction what is happening, the difference in electronegativity between carbon and metal. So this difference of electronegativity is getting decreased. So as the electronegativity is getting decreased, the polarity also getting decreased. So the polarity decreases, going from lithium to magnesium to zinc to copper. Okay. So and the other side, what is getting decreased? The percentage of ionic character. So as the percentage of ionic character getting decreased, you can see here the organolithium will be the highest ionic character here. Of course, the organosodium or the organopotassium will be more compared to this. But in compared to the zinc, I think the lithium has more percentage of ionic character. Okay, so lithium will be more stronger in a reagent in compared to zinc, and the zinc alkyl bonds will be a covalent bonds mostly. Okay, so now we are going to talk about that there will be three different type of organozinc compound we are going to deal in the today's class. One is a dialkyl zinc. You are going to see majorly you are going to see in this particular class that you have a zinc with a dialkyl group here. You have a heteroleptic, so zinc attached with a one alkyl group and another, and one a monoanionic or a electronegative ligand. Okay. So that called R zinc X. You are going to see this class also, and then there will be ionic organozinc compound. So this means there will be a charge, there will be negative charge on zinc. You have seen some of this the diionic compound in case of copper, correct? So first thing, if you are making zinc, generally this is the condition used at the, so it used to use in the beginning. Now there is a better method. If you have this alkyl bromide or alkyl iodide, if you take a zinc dust, okay, so if you take a zinc dust from a bottle, most of the time that zinc dust is not activated, because what is happening, we always mention in the preparation as a zinc powder, correct? But in this zinc powder, there is a lot of times zinc oxide was there, because over the time when it stay there, it become a zinc oxide. So there is a zinc oxide layer. Again, this is a some sort of a heterogeneous reaction happening here. So to remove this zinc oxide layer, sometimes what we do, we start this with a dilute HCl and washing through distilled water, ethanol and absolute diethyl ether before a rigorous drying. This procedure removes the oxide from the surface of the zinc. So that is the one thing we do before we start the organozinc synthesis. The next thing we do, we add some catalytic amount of this dibromoethane. Again, why we add sometimes this dibromoethane, or sometimes we can also add iodine. Again, what is the idea here? Once you add these type of things, this can forms the corresponding zinc bromide and corresponding ethylene, correct? And in case of this dibromoethane, and if you use the corresponding iodine, it can form the corresponding zinc iodide. Once it is forming the zinc iodide or zinc bromide, now the reaction is getting the initiation is started and the reaction started. Okay, so that can help the reaction to move fast. So that's why people use this as a additives. Now there are the dialkyl zinc synthesis can be happen from the Grignard reagent. So now we are talking about, so at the beginning I talk about zinc dust, correct? Now I am talking about, so zinc dust was used as a source of a zinc. Now we are talking about zinc chloride. So if you have a zinc chloride as a source of a zinc, you can treat with a organolithium or a Grignard. That will end up making you this corresponding. So if you treat with the corresponding Grignard reagent, then you end up getting to this dialkyl zinc. Okay, I am going to talk about also the reaction with the organolithium as well. And there is another thing, from zinc chloride, can you make a zinc 0? Okay, that is the what we need, correct? We need the zinc 0 for formation of the organozinc reagent from this corresponding alkyl halides, which I talked about in the last slide. So can you make a more reactive zinc reagent? That is called a Reactive zinc. How that was prepared? That was prepared from a zinc chloride using lithium naphthalate. So you know about the lithium naphthalate, correct? Which is going to reduce the corresponding zinc chloride to corresponding zinc 0. And this is a very reactive zinc. You can purchase the Reactive zinc, and now if you take alkyl halide or alkyl bromide, the reaction happen very fast to form this corresponding organozinc reagent. Okay. Again, there is a functionalized. So this is another very important thing you should understand. Then I am talking about a functionalized organozinc. I think in the previous class, if I talk about a formation of a Grignard reagent, or you have seen the synthesis of organolithium, I never talk about that you can bring a cyanide in your starting material, because it can also get attacked. But here in case of zinc, you can carry some functional group in your nucleophile itself. So that is the advantage of using a organozinc reagent. And now if you treat a dialkyl zinc here, it is going to react in neat condition, both of them to form. So there is a ethyl in the one side, and then this is the functional group in the other side, and there will be ethyl iodide. And slowly what is going to happen, the another equivalent of this corresponding iodide which is going to interact with this and going to form this product. And you can take this for the further transformations. You can use as a reagent for several different transformations. You can have some sort of insertion reaction here. You can have this nucleophile copper. So that means from the nucleophile copper, if you use ICH2 zinc iodide here, this nucleophile can be there could be various different things here. And then if you have, you can able to make, so this nucleophile can able to have a migration from this copper to here. This is a 1-2 shift happening for this nucleophile to get rid of this iodine to form this type of reagent which can be used for several different transformations. So you are generating this copper zinc reagent here. You literally organo copper with bind with this zinc iodide. It can happen, there is a metal zinc transmetallation, as I was mentioning you, that if you have some other things like organotin, organomercury, organolate, antimony, then they can go for a transmetallation within corresponding zinc reagent. So if you have a dialkyl zinc, you take this type of metal halide, so that is going to, what is going to form, that can able to go for a transmetallation, and it can able to form this corresponding mRN. That means you have now different type of corresponding organo. So you have a organotene, or you can able to make all these different type of organotene or organolate. Okay, you can able to make them from starting from this corresponding dialkyl zinc through the transmetallation reaction. Okay. So again in 1864 Franklin reported that the original zinc compound easily can be prepared from the organomercury compound as well. So you take organomercury, also the zinc, here also the transmetallation happening to make the organozinc compound here. Okay. As I mentioned at the beginning, that if you see that if you have butyl lithium and you have corresponding organolithium here. Now this organolithium we talk about, this is called a metal to halogen exchange, correct? And we have learned the generation of corresponding lithium. If you treat the corresponding zinc iodide, it is going to form this aryl zinc iodide. Okay. There will be a huge difference of the reactivity versus these lithium compounds versus this zinc, correct? Again you can see here in this corresponding fluorinated compound formation of the corresponding lithium, and then it can treat with the zinc iodide to get the corresponding organozinc. It can transmetal with a corresponding organoboron compound. It was also become popular that if you have this organoboron compound which you can synthesize from a hydroboration. After hydroboration, once you make this corresponding trialkyl boron compound that can react with this dialkyl zinc. After that the transmetallation happen, you can see this vinyl group transmetallated to vinyl group now go to the zinc. You can able to make this divinyl zinc which can participate in the several different transformations. Another example here, again there is a olefin here. So first hydroboration, and then you can see there is formation of this. You can have some sort of a protecting group for the boron, and then once you treat with dialkyl zinc, it can participate in a transmetallation to form these functionalized organozinc compounds. So this can another way you can bring some functionalizable group. So you have a functionalizable group like let's say you have a cyano with a olefin here. So you can go for a hydroboration, and then that can transfer to the zinc to form this corresponding functionalized organozinc reagent. There could be ionic organozinc preparation. If you take a sodium, that about the sodium can take part in the reaction with dialkyl zinc to form Na zinc Et3. So this can form now you can see the it can form a negative charge on the zinc, correct? You have 3 ethyl now. Okay, so you can see there is a tetra organozincate synthesis here happening from zinc chloride, there is a lithium, lithium wire and corresponding, the halides. So they can form this tetra organozinc, okay? Because here you have, both the side you have a chlorine. So they can now able to form this corresponding, it can form the corresponding lithium, then it is react with the corresponding zinc chloride and end up forming this, okay? There is a formation of a triorganozincate as well. So I think one of the important reaction I already talked about this, that if you have a CH2I2 and zinc activations can able to make this, okay, or if you treat with dialkyl zinc, you can able to make this important species called zinc carbinoid. I think we talk about this when we talk about the carbon chemistry, if you remember. We talk about the discovery by the Bhagwar in Saint-Simon, so and that brings to the Simon-Smith reaction, correct? So this type of the zinc carbinoid is very reactive. Once this zinc carbinoid forms, you can see here the mechanism here. It is going through this the zinc copper. You can going through the insertion first to form this type of corresponding the zinc carbinoid, which can take part in the reaction with the olefin. Now you can see here it is actually generating some sort of a singlet carbene. So through a butterfly like tangent state, it can able to give you the corresponding cyclopropane. You can see here again the mechanism is shown. If you use this zinc copper couple can be used to generation of this corresponding carbinoid, or you can use the corresponding dialkyl zinc which I told you in the last slide. That can also generate this type of the zinc carbinoid species which can able to go to form the corresponding cyclopropane through formation of this corresponding through a butterfly like tangent state. Okay. So here is the example again. You can able to make a cyclopropane, correct? Through this butterfly tangent state, you can able to form this corresponding cyclopropane here. So there is an example here that if you have oxygen here, I think I told you a lot in the carbon part. So you can go back to that part. We talk about several different examples. So that's why I am not discussing any more example after this. You can see if you have an oxygen which can coordinate with the zinc, then it can allow the cyclopropane formation on the same phase of this OH. So that is why you end up getting this product as a major product, okay. Not this is down, okay, this is same side of this oxygen. One of the other important name reaction is the Reformatsky reaction. We learn about this a lot, and I think this comes also in the NET GATE and other exams. So if you have alpha halo esters, so these are alpha halo esters. Once you use the Reactive zinc with them, it's going to form, first you can see there is a halogen, so it's going to alkyl halide, so it's going to form the corresponding zinc. Okay, now you can think about if you have this, and now you can think about this is a two molecules of it. That means the other molecule will have a zinc here. You can think about the other molecule have a zinc, and then you have this the R2 here, and then you have a CO OR. Okay. So you can see this is there is a coordination between this oxygen and zinc, and there is a zinc and this oxygen. So now this can allow to form some sort of a, so you can think about is forming a zinc enolate, and now that can react with the corresponding carbonyl compound, okay. Through a 6-member Zimmermann texture like in tangent state, it can able to form this this compound here, which can after treat with the H3O plus, it can generate a beta hydroxy ester. So starting from a alpha halo ester, you end up synthesizing a beta hydroxy ester, okay. So literally you see this is the part, if you start here, your halogen is gone from here, and it is introduced this part, a reduced carbonyl compound. Again there are several applications. I have shown one of the important application here. If you take this alpha halo ester, Reactive zinc, it will form the corresponding zinc, and then it is going for this analyzation. I have shown in the previous slide, which is going to attack to the carbonyl compound, form the beta hydroxy ester. But after forming beta hydroxy ester, if you treat with the acid chloride like acetyl chloride and pyridine catalyzed DMAF, it will form the corresponding O acetate. Now if you use the sodium ethoxide, it can have two different scenario. It can, I think it can, the most acidic proton is this one. You can able to take this most acidic proton, and it can go for a elimination to get to this type of product with 99% selectivity. So this is what is happening. This could be alternative pathway. So if you write this conversion, what we have learned from here in this particular slide, that what it is from cyclohexanone, it is giving you this product. So you can think about a the Wittig reaction. I think that is the reaction you have learned. I think we are going to talk about that in the when I talk about the organosilicon and phosphorus. So this is an alternative to that reaction here. Okay, it can by using Reformatsky condition also, and then using this acetyl chloride and pyridine, you can able to also get to the, and using sodium ethoxide, you can also get to the very same product. Then the Barbier reaction, I think I talk about the Barbier reaction when I talk about this, the single electron transfer reactions. There I talk about the samarium Barbier reactions and the other chemistry also with indium and others. So here what is happening, if you have this R3 zinc halide, if you have a carbonyl compound, this can participate, this can go for this 1,2 addition. It can, after the protonation, it can form this corresponding alcohol. There are several example. One of the example using this properxylic bromide. If you have properxylic bromide, you put the zinc. It could be the the Reactive zinc, or it could be the corresponding zinc just with these additives. You can able to make this corresponding the zinc reagent, and now if you treat with this corresponding aldehyde, it will going to participate a Barbier coupling to form this corresponding alcohol, which can be protected from this compound, which can be finally after a few steps to convert to a very important compounds. So what is the things here? The important thing here, what is the difference of this reaction compared to a Grignard and others? Here what you are happening, you in case of Grignard, you have to make the Grignard first and then you have to add, correct? If you want to add to a carbon compound or something. But here you can take everything together. You can take this reagent, aldehyde and the zinc. There will be no interference. So zinc will going to only react with the properxylic bromide to make the organozinc, then the reaction will happen with the aldehyde. Blaze reaction here, again you have this alpha bromo ester. We have already learned about the alpha bromo ester to formation of the organozinc, but now you have this is your nucleophile, you change your electrophile. Your electrophile previously in case of Reformatsky was ketone, now it is a corresponding cyanide. We know that the Grignards or this lithium attack also cyanide, here the organozinc also attack here, and it can form this type of chelation complex here. And from there, once you treat with the K2CO3 and 1 molar HCl, it end up forming a beta keto ester. So starting from the alpha halo ester, you end up synthesizing a beta keto ester. Again, what is happening, if you understand there, the halogen is gone, this alpha bromo halide is gone, and you end up this carbonyl group. So remember, if you give these conditions where you treat with the corresponding cyanide, then you remember that you have to just introduce RCO group and replace the bromide, and that will be the product, correct? If you see this type of problem in the exam, that's how you should solve this. Okay, then you can see if you have this type of copper species which can be synthesized. I have mentioned using this zinc iodide and this copper, and you have seen those type of species generation. And if you try to go for the copper, can go for this again this organocopper region, we have learned it can go for some sort of a 1,4 addition. But if you use a Lewis acid here, okay, like a BF3 etheret, then what is going to happen, then you end up finding a 1,2 addition happening, because once you activate this carbonyl more with a Lewis acid, now that particular carbon will be more electrophilic. That's why you see formation of this 1,2 addition product instead of the 1,4 addition which is happening in other case. There is a enantioselective version of this 1,2 addition reaction. We have learned this dialkyl zinc can add here, correct, to the aldehyde. Now can this reaction be asymmetric? Yes, if you use a chiral ligand. So this 3-exodimethyl amino isobutanol, there are so many variations of this, where you can see there will be nitrogen and oxygen, this type of ligands was developed, a lot of them was screened, and this is found very good for this reaction, giving very high enantioselectivity. If you try to understand the transient state, again you can see in the corresponding transient state the zinc is binding with both nitrogen and oxygen, so there will be two different zinc. Okay, so you can see the one is binding with this amino alcohol here, so this is the one, and the other one is actually here, which is binding with this corresponding with the substrate. So this oxygen is binding with this oxygen and the substrate oxygen here. Okay, so that's how you can see in this particular transient state, you can see these are all kind of formation like a chelate, and that's why this R group from the zinc going to transform to the particular phase of this carbonyl. So you are kind of using the chiral ligand, you are blocking one of the phase of this carbonyl group here to get to the product with a high enantioselectivity. Okay, there are the reaction of functionalized organozinc reagent using copper salt. So you have a functionalized group, you are able to make them using the copper cyanide and L lithium X. You can able to make this RCU zinc X, and then you can use this type of reagents for, or you can use a dialkyl zinc here, functionalized, use copper cyanide, and then you can I think you can able to make this this reagent as well, where you have a copper and a zinc, okay, with a copper cyanide and zinc. So this can be used for several different transformations. One of the things is showing here. If you have this corresponding aryl bromide, okay, you first make corresponding zinc chloride. So you treat with the lithium naphthalate and zinc chloride, that will end up forming first. And now if you treat with the copper cyanide, it will going to make this copper CN zinc bromide, okay, and this is much more reactive compared to a normal organozinc reagent. So it can now take part in acylation reaction with acyl chloride to form this product. So some of this reaction was some of this reagent was developed by Professor Nochels, and he has a lot of contribution development of different type of organozinc reagent. Again there is another example here. If you make this corresponding organocopper zinc species, as I mentioned, you use zinc dust, then you use the copper cyanide. If you remember the copper cyanide effect when you make the when I talk about the formation of the organocopper reagent, if you remember, and so that is the Lifshitz reagent, if you remember, they those are very reactive. So very similar tricks are happening here to forming this this type of compound here. So now they are forming this corresponding copper reagent using the first they are forming corresponding zinc. Now there is a transmutation happening to form the corresponding organocopper, and that's how they are able to keep this different type of functional group here that can add to the corresponding aldehyde. Again there is a from the Cram's rule, it is going to attack. So there will be a large, medium, small, and it is going to nucleophile going to attack from where it will be where there will be a smaller or medium group. That's how the nucleophile should be attached. Okay, that is shown here to give it to this product as a major product. Again there is another example here, this corresponding iodo in place of zinc dust formation, this organocopper species, which can now take part in a 1,4 addition. If you have organocopper compounds, you have learned in the previous lecture that it can take part in the 1,4 addition, and TMS chloride is also very important. So sometimes TMS chloride is playing a very important role because it can also able to activate this carboning. Okay. So this can generate some sort of a delta plus that can allow this type of 1,4 addition happening faster. Then there is another important cross coupling reaction. So I started about the Kumada, and then I talk about the Kumada coupling, I talk about the Sonogashira coupling in the last class, and now I am going to talk about another important coupling called Nigisi coupling. So Professor E. Nigisi, okay, he was a faculty from Purdue University. So he received the Nobel Prize in 2010. Okay. So there was Professor Heck and then Professor Suzuki. So this three of them shared the Nobel Prize for development of this cross coupling reaction. Again, you can see you can use a palladium catalyst or a nickel catalyst. What you have organozinc and you have a corresponding aryl halide. Of course, this reaction has went to alkyl halide, and there are lot more scope, but I am going to only talk about the reaction. You have some sort of aryl halide here, and it can participate in oxidative addition. You know that if you take a palladium 0, it will take part oxidative addition to make this palladium a palladium 2 complex. I think there will be a palladium 2 here. Sorry for the typo here. It will be palladium 2, guys, and then there will be transmetalation with the corresponding zinc reagent first, and then there will be reductive elimination to get to the corresponding product. Okay. Again, it is a very similar mechanism. What you are seeing, we are changing the transmetalation agent. Here we are only changing the zinc. Okay. So when it is a Grignard, it is a Kumada. When you see it is a alkyne with a copper acylate, it is the Sonogashira. And you are going to learn that when it will be the boron, it is the Suzuki, and when it is a zinc, it is going to be the Nigisi coupling. Here are some example. Here you have this alkynyl iodide and you have this corresponding vinyl zinc, which is going to take part in the Nigisi coupling with palladium 0 to form these corresponding enions. It can also use corresponding zinc bromide, and corresponding aryl iodide also can form the biaryls. Another important coupling is the Fukuyama coupling. So you can see it is the another version here. Instead of using this the aryl iodide, here they are using a thioester. So what is happening? Palladium first can go for a oxidative addition reacting with the thioester here. So with the thioester it can go for oxidative addition, then after that thing is transmetalation happening with the organozinc. That is the very similar with the Nigisi coupling. Then formation this palladium 2, and then there will be reductive elimination happening. So you end up from a thioester, you are making a corresponding ketone. You are replacing this SAT with a R1 here. Okay. And mechanism will be very similar, correct? So oxidative addition, transmetalation, and reductive elimination. Okay, there is an example of Fukuyama coupling given. You have this, it can also work with this alkyl zinc. Okay, it can also work with alkyl zinc reagents. You can think that there is a example here with this corresponding the thioester. So that the corresponding thioesters, yes. So you can see the thioester is reacting with this corresponding organozinc compounds. In place of the palladium, appropriate ligand to get to these corresponding carbonyl compounds here. There is another example. You can see the alkyl zincs are participating in a transmetalation reaction here. In place of the palladium, what is happening again? You have these corresponding thioesters. So that can now what is happening here? The thioester is actually in case of using this reagent, it actually forming this product after the first cross coupling, and then this it can able to remove the OH group here to get to the biotin, which is a very important compound here. Okay. So in the next slide we are going to talk about the reaction using the organozinc copper reagent. So there is another important reaction here. You have this alkyne here. If you have this corresponding, you have learned that the corresponding copper zinc, you have learned about the carbocupration here to the corresponding acetylene. Here you have this alkyne, it can go for a carbocupration here first. Again you can see this the corresponding copper and this functional group add in the syn fashion to the alkyne. Then you treat with the ICH2 zinc iodide, there will be a 1,2 shift going to happen here. So there is a 1,2 shift happening for the formation of this type of allylic copper species. Now this allyl copper species can participate a reaction with a carbonyl compound through a 6-member tangent state. They can form this type of cyclic furanone. Okay. Again, here are the references for these courses. I think please go through these references that can give you some of the important books for which introduce the organozinc chemistry. And again, thank you so much for coming to the class, and I am going to see you guys in the next class. Thank you.